Hey class, this is Adam Ward, and I wanted to talk to you today about the general solution for a CSTR. This follows out of Lecture 3 in your textbook, specifically Section 3.3. You should have already watched a video of me talking to you about how we do a mass balance and some steady state solutions that look an awful lot like our simple equation from the first lecture. What we're going to deal with right now is, what if you're not at steady state? So what if dc dt does not equal 0 and we can't make that simplification that we made in the previous video? So that's what we'll talk through. What we're really asking today then is something about the temporal aspects of pollutant reduction, or really how does the system respond? Not where does it eventually get to, but how does it get there and how long does it take to get there? Let's look at a simple example to help illustrate what I mean. So let's say that our loading looks something like this. So that's a plot of loading through time on the top and concentration through time along the bottom. And so for this first bit, until you get to the first gray dotted line, there is no load and there is no concentration. So you're at the past steady state, or the previous steady state conditions. Now for whatever reason, at that time, a new load is applied. Now if that load is applied for long enough, we may get to some second steady state or some new steady state. But how do we get there? Right? It is possible then that we remove that load at the second dotted line and we get to some other steady state. What we're interested in today is not those steady state conditions, but how we move between them. So, for example, does the lake instantly come up to its new steady state concentration and just remain there during the load? Does it connect the dots in a linear fashion? Does it grow in exponentially? And I have the same questions as we think about how we go from that higher steady state back down. These are the questions that we want to be able to address today. Right? We want to take those question marks and turn them into something that we can predict. So the model I'm writing out right now is what we looked at last class. Accumulation on the left-hand side equals loading minus outflow minus losses due to reaction minus settling. And we'll make one adjustment today. We're going to divide both sides of this equation by volume, and so when we do that, we get the equation at the bottom of the slide here. Great. So we've got an equation. What do we do with it? We can describe the system in what we call an eigenvalue. An eigenvalue is a characteristic value that describes the system. It tells us something about how the system itself responds due to its characteristics, but independent of what the loading might be. And so we can rearrange the equation from the previous slide to look like this. Now what have I done here? I've moved the outflow, the reaction, and the settling all together and factored out a concentration, and I've separated the loading on the left side from the accumulation and the outputs on the right-hand side. So we've just reorganized using algebra from the previous page. So the bit that I'm highlighting in red right now, this is how the system responds to loads. Right? If the loads are on the left, the right-hand side is telling you the response to those loads, or how the system balances out the loads that are applied. The chunk that are in parentheses, we call this an eigenvalue, and Chopra uses lowercase lambda to represent that. And all it means is a characteristic value of the system. Literally, it is a value that describes the system characteristics. That's what I want you to know about lambda. Now, one thing that sometimes throws people off in this class, they say, oh, isn't that the assimilation factor? Strictly speaking, no, it's not. So I've written that in orange at the bottom. Lambda is not an assimilation factor. Lambda is an assimilation factor divided by a volume. I know that seems a little bit arbitrary here, but you remember the previous slide, we just divided by V. And so strictly, it's not an assimilation factor, and it definitely has different units. You might ask yourself, what are those units? When I look at lambda, I look for the simplest term. I see a first-order reaction rate. So lambda has the same units as that first-order reaction rate. It's 1 over time. Now we're going to do what we call the general solution. And so this is the solution for time periods when loading is equal to 0. Now, this doesn't mean that the system is at steady state. It simply means that we can zero out the left-hand side of the equation we just wrote down. So it's non-steady state, but it is allowed to vary in time, and there is no load. And so if we take our previous equation, we zero out the loading because there was no load, what we get is a fairly simple exponential equation. If you want to go through the calculus, you're welcome to. If you want to have faith in me doing it, that's fine. We go through separation of variables, we integrate, and what we find is an exponential decay. The concentration at any time is equal to the initial concentration, C naught, times e to the minus lambda t, where that t is time. So graphically, this equation looks something like this. The bigger the lambda, the more efficient the system is at removing mass. You get curves that look like the black curves that I've drawn along the bottom of that axis. As lambda gets smaller, the system acts more slowly on a load, and so it'll take a lot longer for that system to empty itself out of the pollutant or to have that concentration decay back down towards zero. So the bit that I've boxed in red is what we call the general solution for our system. This describes how our CSTR will behave in absence of any loading. So this only applies when W equals 0. Now you might say to yourself, well, there are a whole lot of systems where W is non-zero, right, where there are loadings. You're absolutely right, and you are jumping ahead to lecture 4 in our textbook, and we'll talk about that in the next video as well as the next class. Thanks for your time, everyone, and I hope this helps.